Log on, tune in, find out. Another good idea from Cambridge.
Clock there, it's 3:30, so we should make a start on the afternoon session. So my name's Barbara Holland. I've been asked to chair. If you're giving a talk, I'll give you a 5-minute wave, and then at 2 minutes I'll stand up and start to look menacing. With no minutes to go, I'll tackle you off. Great pleasure to welcome our first speaker for this session, Katharina from University of East Anglia. It's going to be talking about mole trees.
Thank you, Barbara. Can everybody hear me? No. I don't know, the red light is on.
Keep talking, I'll go stand at the back.
Any better? Any better? No. Red light is on. What are you going to do?
Just start.
Go to the last slide. Anyway, welcome back to my talk. Now I want to talk about comparing mole trees, and I think the first thing I should maybe talk about. Can't hear me. Okay.
Mic may not be on.
It is. There's a red light on.
Yeah. On.
Should
I just start, and I'll just try and ask about.
Any better? No. Okay, I just start. Anyway, so I want to talk about comparing mole trees, and the first term you might not know about is what a mole tree is. And these objects arise in the context of studying, for example, the evolution of polyploid species. And examples of mole trees is what you see here on my slide. And they were produced in the context of a study by Bengt Oxelman on a Silene data set. Silene is a special type of plant. And the main difference of this kind of tree to a phylogenetic tree is that, for example, this leaf and that leaf here has the same label. And that's what is a characteristic of multi-labeled or multi-labeled trees. Now, when Bengt talked to us about how could actually a evolutionary path of, say, a data set like this look like, he was thinking of a network-like scenario. And after some time, we actually came up with an answer, meaning we did come up with a method that could actually explain these kind of evolutionary relationships you see in these mole trees. But this method has an input in the form of a consensus mole tree. Now, as I already said, a mole tree is slightly more general than a phylogenetic tree, and actually there's a number of consensus methods for phylogenetic trees known, but if you want to do this for mole trees, then a lot of things can go wrong. And my PhD student, Ratsukikis, has a poster out there, I think tomorrow, where he's actually talking about a method to construct these mole trees. Now, when we were talking about, or when we started to study these mole trees, we were soon realizing that actually for an input data set, you can have many, many different mole trees. So the next question for us was then, well, how can we compare them? And that's where my talk is coming from, namely we want to compare these mole trees. Now, what you see here on my slide is two extreme situations for mole trees. Namely, on the left-hand side, you see a phylogenetic tree on the set X from A to F, so that's my leaf labels. And to the right, you see also a tree, but all the leaf labels are the same. That's an example of a tree shape. So these are the two extreme situations. Now, although I realize that some of you might find this rather boring, I just wanted to remind you of the definition of a metric. So I have a class of mole trees with leaf set M being a multiset. Then a metric is just a map from Tm cross Tm into the real numbers. We assume them to be non-negative. Should have put this on there. So that the distance between any two mole trees is 0 if the mole trees are the same. My distance is symmetric, and I have the triangle inequality. Now we call a metric proper if I have that the distance between mole trees is 0. This implies that my two mole trees T1 and T2 are isomorphic, with isomorphism between mole trees being defined in the obvious way. So bearing in mind that phylogenetic trees are very similar but also very distinct from phylogenetic trees, what kind of metrics could one think of? And one metric, for example, is the cluster metric. Now, if you go back to phylogenetic trees, the cluster metric just says, look at every vertex of my tree, this one here, this one, and so on, and look at all the vertices, all the leaves that can be reached from that vertex. So, for example, my vertex V, to this vertex I can associate the cluster A, B, and C. Now, if I do this for every interior vertex, then I get my set C of T1 for this tree, and C of T2 for that tree, and then I just take the symmetric difference, divide by 2, that's my cluster metric. Okay, just like you do for phylogenetic trees. Now, this is actually not a proper metric for trees, because you don't have that. If the distance is the same, then there must be isomorphic. The counterexample is provided by tree shapes, i.e. trees that have all the labels the same. Now, for phylogenetic trees, the cluster metric coincides with the Robinson-Foulds metric. And that's defined as for any two trees, take this tree and that one again, which are the same as the ones we had before, then the Robinson-Foulds distance is just the minimum number of edge contractions and vertex expansions to transform this tree, in my example, into that one. And in this case, my Robinson-Foulds distance is 3. So we have already seen two metrics. What other metrics are out there, or distances? Well, there is, for example, the nested label metric that was introduced, I think, by Louis Nacle, worked on by Gabriel Valiente and co-workers. And this is also a distance on my tree set. Namely, what you do is, for every vertex, say you start off with the leaves, and so with the leaves, to every leaf, you just write for every vertex, when you start off with the leaves, you just define its nested label to be the set containing that leaf. And if I have an interior vertex, then, and I have my V here, for example, then you define the nested label of V to be the nested label of this child and the nested label of that child. So, for example, for my vertex V here, its nested label representation would be that structure here. Now, I realize that all these brackets are rather confusing. What you should maybe think about when you think about the nested label representation of a tree is the Newigg representation. Okay. Now, of course, I can do that for this tree, and I can do that for that tree, and again take the symmetric difference, divide by 2, I get a measure, which is then on the class of trees a metric. So that's another one. And for these two trees, my nested label distance is 4. Remember, for the Robinson-Foulds distance, the nested label distance, for the Robinson-Foulds distance, for these two trees, the distance was 3. So we already see that there is some difference. Now, another metric one could look at, and which has been looked at by, I think originally by Tandy Won and Mike in a 1990 paper. It's the maximum agreement subtree distance, and also more recently in a phylogeography study. Is this correct? Tandy?
You're not the first people to look at this.
I know. I mean, I know that you did it with Mike in the 1990s, and then there was a recent paper in a phylogeography study. That's when we saw it again. But there might be some people in between, so please let me know if I forgot to mention somebody. So what is that? Well, for each, I again look at my two trees, and then I define the distance between my two trees as just the number of elements in my leaf set M, with multiplicities minus the number of leaves in the maximum subtree for the two of them. So, for example, if I look at my two trees again, then if I forget my D here and its pendant edge, and I forget the D here and this pendant edge here, then my two trees are the same. So my the leaf set side of my maximum subtree is 6. I have 7 leaves altogether, so their distance is 1. And their mass distance is 1. So again, it's a completely different answer from the Robinson-Foulds distance and also from the nested label distance we had before. Now, another distance, which is not the same as the one I think Valiente and co-workers were looking at, is the triplet metric. So what is the triplet metric? Well, if we again go back to phylogenetic trees, then we can look for each trees, like for this one here, at all the triplets, which is rooted subtrees of size 3 that are displayed by my tree here. Okay, all of them. Now I can look at the triplet distance between two trees as just take all the triplets induced by them, take the symmetric difference, divide by 2. That's the triplet distance. But the point is, we are now not looking at phylogenetic trees, we're looking at multrees. And some leaves can have the same label. And that makes a big difference. Because what we have to do is, we have to now, firstly, look at all possible ways of making these two leaves, I have an A here and an A here, distinct. So in other words, we have to look at all what's called a consistent relabeling between this tree and that tree, and then just take the minimum of the triplet distance of these two trees, where the stars are just my T1 star is a consistent relabeling of T1, and T2 star is a consistent relabeling of my T2. So I look at all of them and then look at the minimum number. Now for my example, if I look at the triplet distance, then for these two trees, I get 4. Now, we have seen the 4 before. Now, if I remember, the Robinson-Folds distance was 4 for these two trees. So we see already that some of the distances are the same, and some of them are larger, and sometimes they're also smaller. And I will get back to this at the end of my talk. Now, another distance one could think of in the terms of comparing trees is the rooted subtree and prune, rooted subtree, prune, and regraft distance, which Maria Bonnet already talked about, well, in some sense, earlier today. So what you do here is you just apply the rooted SPR distance. You just transform this tree into that tree by just applying rooted SPR moves, and the minimum number then of these rooted SPR moves to transform my T1 into my T would be my distance now. And if I don't look at rooted SPR moves but NNI moves, then I would get the NNI distance between my two trees. So for this example, the SPR distance is 1 and the NNI distance is 3. Again, both these numbers we have seen already. So now this is one of the main results I wanted to talk about very briefly. Namely, I already mentioned to you all these distances, and I already pointed out to you that some of these numbers are the same. And it turns out that there's actually a very nice domination relationship. Namely, so this domination relationship is summarized in this slide here. So for example, if I have a pair of trees and I want to, then I know that the Robinson-Folds distance between them is larger than the cluster distance. Cluster distance. It's also larger than the SPR distance, but the triplet distance between these two multrees is the largest one. Okay? So the fact that we observe that these numbers are sometimes the same, sometimes larger, this is actually not a coincidence. There is really a very nice relationship between these numbers. Now, once we had established this one, we thought, well, what is the diameter of these various metrics on my set of multrees? Because if I know the diameter, I can kind of understand what's the worst case. What are trees that are furthest apart, which I then can use for normalization purposes. And what we found is summarized in this slide, which looks unfortunately rather full. So let me just try and walk you through that slide. So suppose we have a multiset M, and we assume that the size of this multiset is larger than 3. Now, if my distance is either the cluster distance or the Robinson-Folds distance, and I'm in the situation that my multiset M doesn't only consist of just A's, but of A's, maybe 5 A's, 3 B's, and some C, whatever. It's just to make sure that not every element, the multiplicity of an element is not the size of M. Then we know that for the binary multrees on M, the cluster distance or the Robinson-Falls distance has diameter bound the size of n minus 2. And if I also allow my tree shapes, which are excluded here, then the diameter bound is for the set of binary tree shapes with n leaves is on, now I'm talking about the multiset size for these two metrics is actually given by this bound here, which is slightly more complicated than what I see if I exclude the fact that my multiset M only consists of just one element with a high multiplicity. Now, if I look at the nested label distance, or nested label metric, dn, then I can also talk about the diameter. I can actually really put my finger on the diameter of that metric on the set of binary multrees. Namely, if I have a tree shape that only has 3 leaves, then the diameter is 0. If I don't have, if I have an element that is, if I have an element, if not, I don't have an element whose multiplicity is the size of m, then I get this bound here, and otherwise I have this even smaller number here. Now finally, we also were talking about the maximum agreement subtree distance, and for the maximum agreement subtree distance on the class of binary multrees, the bound is given here. Now, that's actually all I wanted to talk about, because I thought that's quite a nice story, because I'm very excited by the fact that firstly we have these diameter bounds, and secondly we have these very nice domination relationships.
Great. Left time for questions.
So I guess I'm sort of trying to think about whether or not there's anything non-trivial about extending these concepts to trees that where you care about branch lengths as well.
Mm-hmm.
So all of these distances are based on topology.
That's correct.
For topology only,
That's
you've got
correct.
these nice domination relationships. What happens, if anything interesting, when you add branch lengths?
We haven't looked at that. It's a very interesting question, but our problem already is that what is very important if you want to, for example, do a consensus tree from phylogenetic trees, what you do is you can break up your input trees into a set of clusters and then just look at the union of all these cluster sets that you get from your trees and check if that set is compatible, and if so, you can construct yourself, for example, a consensus tree. Now, if you want to do this for multrees, you're in big trouble. You can't. It's NP hard to decide whether a given collection of multisets actually fits onto a tree or not. And therefore, we were only focusing on topology. First, in order to understand the topology a little bit, the results for topology better, before we were thinking of extending to trees with branch lengths, because already the topology type problems are very difficult. Yes, please.
Just to clarify, this domination relationship also holds for uniquely labeled trees, not mult trees, but just normal.
If
what
you
I
have
call normal.
phylogenetic trees, then for example, some of these errors like the Robinson-Falls distance and the cluster systems, cluster distance, they coincide. They're the same thing.
Yeah, okay, so there
Yep.
existence like that.
Last question?
So I guess I'm trying to understand the kind of data on which this will be used. When you talk about biogeography and so on, there would be additional labels where things say A, but actually they mean something different. And exchanging 2 leaves, although they're both A, would actually have a meaningful.
Yep.
So in what sense do we identify those two to really call something a multree?
Well, we were thinking in terms of these multrees when we were looking at trying to understand the evolution of polyploid species. And for these species, but now I have to refer you to Bengt, who knows more about that than me. Bengt is sitting over there in the last row. What happens there is that you have nuclear genes and molecular mitochondrial genes. And for both of them you have information. And this kind of information you want to, in the sense of gene trees, and these you want to put into a consensus tree, a consensus multree, because you have multiple labels which you have to deal with. And that's where we are coming from. So the fact that this maximum agreement subtree distance is also used for biogeography it's a nice link, but we were not looking at them in this context.
Just
No, you cannot.
We'll talk about it later.
Told by Vince I have to keep everyone to time, so sorry about that. Thanks, Chris. Thank Marty.